In this lecture, we'll introduce and derive and describe some applications of a really useful relationship in electrochemistry called the Nernst equation. We'll start out by considering a voltaic cell, meaning a battery, running on the now very familiar spontaneous redox reaction of zinc metal being oxidized by copper 2 plus ion to zinc 2 plus ion and copper metal. We know that the potential for this, overall potential for this reaction under standard conditions is 1.1 volts. Now the overall potential, remember, is sometimes referred to as the reaction driving force or the electromotive force or EMF. But in any event, of course, the superscript 0 means that this is the driving force under standard conditions, and standard conditions would be 1 molar solutions and elements in their standard states. So we have zinc and copper solids in their standard state, which would be a solid, and copper 2 plus ion at 1 molar concentration and zinc 2 plus ion at 1 molar concentration. Now, as this reaction proceeds, it makes sense that the copper 2 plus ion concentration will decrease as the reaction goes left to right, and the zinc ion concentration will increase. So let's let this reaction go to 99% completion. If that happened, at that point, we'd expect the concentration of copper 2 ion to be just 0.01 molar, and the concentration of zinc 2 plus ion to be 1.99 molar. And one might ask at this point, what's the cell potential now? Well, the copper 2 plus, again on the reactant side, has dropped to 0.01 molar, while the zinc 2 plus concentration on the product side is increased to 1.99 molar. No one would argue that it would at least make sense that at this point the driving force for the reaction would be less than 1.1 volts, less than when we started at 1 molar each. So you notice when I write here, what is the cell potential? We don't have the little superscript 0 because we're no longer under standard conditions. Standard conditions would be 1 molar solutions. So how can we calculate the real cell potential at these actual concentrations of copper 2 and zinc 2 ion that are present at this point after 99% of the reaction has been completed? Well, that's where we bring in what's called the Nernst equation. Well, what does the Nernst equation do for us? It allows us to calculate the dependence of the cell potential on the actual concentration or concentrations of redox components in the voltaic cell. So here is the Nernst equation. We have the actual potential, which I've labeled E cell, no superscript 0 because it's not under standard conditions, will be equal to the E cell, the cell potential under standard conditions, minus an adjustment for non-standard conditions. Well, what are these terms in the adjustment for non-standard conditions? The 0.0592 volts, the capital V is for volts, this is actually a constant which is derived from the gas constant, the Kelvin temperature assumed to be 298 K, and Faraday's constant. N is the number of electrons transferred in the balanced redox reaction as written, and as you know well by now, for this particular reaction, N equals 2. And Q is the what should now be familiar reaction quotient. This is what has the same form as the equilibrium constant, but uses actual concentrations at the present time. Now for this example, the reaction quotient would be 199 because it would be the concentration of zinc 2 plus over the concentration of copper 2 plus. Remember, the solids, zinc solid and copper solid, would not appear in the equilibrium constant, so they don't appear in the reaction quotient. And we have 1.99 divided by 0.01, or 199. Well, let's finish this calculation on the next slide. So we have the Nernst equation, and for our copper zinc voltaic cell, the standard potential we know is 1.10 volts. We know that N equals 2, and at 99% completion, Q is 199. So we can now calculate the actual potential under these current conditions, and we'd have 1.1 volts minus 0.0592 volts divided by 2 times log to the base 10 of 199, and we end up subtracting 0.068 volts from 1.1 volts, and we get an actual cell potential of 1.03 volts. So yes, our battery is starting to run down. At 99% completion, the driving force for this reaction going from left to right is less than it was when all the solutions were under standard conditions or 1 molar concentrations. Let's see if we can go back and derive the Nernst equation. I suspect that you probably can see that it looks a little bit familiar, meaning that it looks similar to something that you've seen before. The Nernst equation actually has its origins in the calculation of the free energy change for a chemical reaction under non-standard conditions. Recall the following: the actual free energy change equals a standard free energy change plus an adjustment, the adjustment being RT times ln of Q, where Q is the reaction quotient. Also recall that there's a relationship between the free energy change and the standard potential. Delta G0 equals minus NFE0, which means by extension that the non-standard delta G equals minus NF non-standard E value, the potential under non-standard conditions. Now if we substitute these two expressions in for the delta G0 and the delta G into the equation from the chapter on thermodynamics, we get minus NFE equals minus NFE0 plus RT ln of Q. Well, if we divide everything through by minus NF, we'd be left with just E on the left, then E0. This term RT ln of Q divided by minus NF would result in a term of minus RT ln of Q over NF, which I'm rewriting as minus RT NF all times ln of Q. Now, for reasons that aren't altogether clear, historically, electrochemists have preferred base 10 logarithms in the Nernst equation rather than the natural log. So we will convert to base 10 logs using the following conversion factor, that the ln of Q equals 2.303 times the log to the base 10 of Q. If we put this in the equation that we derived so far, we get an expression that looks like this. And at this point, we can recall that the gas constant in energy units is 8.314 joules per mole per K, that the temperature is 298 K, and you say, how do we know the temperature is 298 K? We're just assuming that it is, because that's a very common temperature. What we're getting at is a way of simplifying this expression so it looks like the Nernst equation that we used in the example calculation, the first problem we did. We're trying to get this 0.0592 volts over N expression. So if we assume the temperature is 298 K, and that we remember Faraday's constant is 96,485 coulombs per mole, which would be equal to 96,485 joules over volts times moles, then we can actually simplify the Nernst equation even more, and combining F and R and assuming T equals 298, we get this expression here that the actual potential is the standard potential minus 0.0592 volts over N times log to the base 10 of Q. Now, if you wish to add the subscript cell on these capital E's, you can do that. E cell equals standard E cell minus 0.0592 volts over N times log of Q. It's not necessary. If you just wrote E, I'd know what you meant. If you wrote E0, the important part of that is the zero part, not whether or not you've said cell as a subscript. Okay, let's do another example. Consider this redox reaction, which is actually the oxidation of iodide ion to iodine, the element, by the good oxidizing agent dichromate in an acidic solution. And what we want to do here is we want to calculate the EMF, or the potential, at 298 K when the concentrations are as written here. The dichromate ion at a concentration of 2 molar, the hydrogen ion at a concentration of 1 molar, which by the way means the pH would be 0. The iodide concentration is 1 molar, and the chromium 3 plus concentration, which is on the product side, is very small, 1 times 10 to the minus 5 molar. Well, to do this, we of course are going to use the Nernst equation, but we have some work to do before we can get this answer that we're looking for. First of all, we're going to need to find E0, the standard potential, using the table of standard reduction potentials. We're going to need to determine N, the number of electrons transferred in the balanced redox reaction as written. And we need to determine the reaction quotient Q using the given concentrations here. Now, of course, it's quite useful and helpful if you understand what's oxidized and what's reduced in this reaction. Now, I told you that at the beginning of this slide, but if you were unsure, of course, what you'd want to do is assign oxidation numbers. Good practice to do anyway. So if we assigned oxidation numbers, we'd remember that oxygen is -2, which means that the chromium in this case would be +6. 2 times a +6 is +12. 7 times a -2 is -14, which you add those up and it leaves -2, which is the charge on the ion. Of course, the oxidation number of hydrogen ion would be +1, of each iodide ion would be -1, of each chromium 3 plus ion would be +3, of iodine the element would be 0, and here oxygen would be -2 and hydrogen +1 in water. So it appears that each chromium atom in the dichromate is reduced by 3 electrons from +6 to +3 for a total of 6 electrons, because there's 2 chromiums. And the 6 iodide ions go from -1 to 0, so they're each oxidized by 1 electron for a total of 6 electron oxidation. So we can see that it's clear from this that N in our Nernst equation will be 6, so we've completed task number 2 on the original list. Now we can break out the relevant balanced half reactions here. The oxidation half reaction would of course be iodide being oxidized to iodine and losing 6 electrons. And that would be the anode, because that's where oxidation takes place. And the reduction would be dichromate being reduced by 6 electrons, and the reaction involves hydrogen ions to produce chromium 3 plus in water. And since this is where reduction occurs, this is the cathode. And what we'd want to do here is use the table of standard reduction potentials and calculate what the standard potential would be, the E0, for this reaction. That would be task number 1 here. So that we don't have to put the whole table on the slide, I've drawn these entries from the table, and you can see that the reduction of dichromate to chromium 3 plus is favorable by 1.33 volts. The reduction of iodine to iodide is favorable by 0.54 volts, but of course we're looking at the oxidation of iodide to iodine, so we'd reverse the sign here and be minus 0.54 volts. You might also, and we would add those together, you might also recall that we could use that simple equation of taking the table value for the reduction at of the cathode reaction and the reduction potential for the anode, and we could then say 1.33 volts minus 0.54 volts, reading them right off the table, equals 0.79 volts. We would have gotten the same answer by just reversing the iodine reaction here, which we would, and change the sign of 0.54 to minus 0.54 and adding these together, get 0.79 volts. So 0.79 volts is the standard potential. And so now we've completed task number 1, because our standard potential E0 is 0.79 volts. We now have one more task, that would be calculating Q. So we'll put the problem back up here and we'll go about calculating Q. Remember, Q has the same form as the equilibrium constant, and we take the concentrations of the products raised to the power of their coefficients. The only product we can use is chromium 3 plus, because iodine in this equation is in as a solid, water is a liquid. So we take the concentration that we were given of chromium 3 plus and we'd square it. All 3 of the reactants can go in the denominator here. So we'd have the dichromate concentration of 2 molar, the hydrogen ion concentration of 1 molar to the 14th power, thank heavens it's a 1 there, and the iodide concentration, which is 1 to the 6th power. Again, thankfully, we didn't have to do that math. So you can see it's simply 1 times 10 to the minus 5 squared divided by 2, which turns out to be 5 times 10 to the minus 11. Since previously we determined that N was 6 and that the standard potential was 0.79, we can solve for the actual potential here. It would be 0.79 volts, the standard potential, minus 0.0592 volts divided by 6 times the log of 5 times 10 to the minus 11. And when we do the math, we find out that the voltage is 0.89 volts. So you can see that the potential or driving force or EMF or voltage, whatever you want to call it, in what we've labeled as E or just E cell, for this redox reaction is more positive at the stated concentrations of the problem than under standard conditions where all the concentrations would be 1 molar. Now, if you recall Le Chatelier's principle, this actually makes sense, that the potential would be higher here for this set of conditions, because what we've actually done with our actual concentrations given is that we have loaded up the reactant side relative to what the concentration would be under standard conditions. So instead of 1, 1, 1, and 1, we have 2, 1, 1, and 0.00001. And under those conditions, the potential is even higher. And if you think about this in terms of Le Chatelier's principle, when we load up the reactant side relative to the product side, it would make sense that the potential or the driving force for the reaction would be even higher than if we had relatively equal concentrations on both the reactants and the product side. In the next part of this lecture, we'll go on and look at some more applications of the Nernst equation.